Welcome to the Hidden Brook Technologies presentation on HDL Rhetoric. A hardware description language, or HDL, such as Verilog or VHDL, is used to describe the structure of logic circuitry. HDLs stand in contrast to programming or scripting languages such as C or Python. While programming languages consist of executable instructions that tell a microprocessor what to do, HDLs consist of descriptions of functions that tell logic circuitry what to be. Programming languages are like to-do lists, whereas HDLs are like blueprints. The circuitry defined by the HDL is brought into existence either by custom silicon manufacture in an application-specific integrated circuit known as an ASIC, or by programming the configurable interconnections of the circuit elements in a field programmable gate array, also known as an FPGA. Once the design is up and running, the instantiated circuitry then does whatever its design has ordained that it must do. In this way, HDLs are somewhat like DNA. DNA does not provide a set of instructions to an organism that tell it what to do. DNA determines what an organism is. How the organism then behaves must follow from whatever has been brought into existence per the text of the DNA. Will it conduct photosynthesis? Will it have a nervous system, endo or exoskeleton, pack behavior, or solitary? An adage from my high school biology teacher was, "Structure determines function." And it's as true in electronics as it is in macro, micro, or molecular biology. Now, the capacity of programmable logic ICs is now sufficiently large that a portion of the circuitry defined in the HDL can in fact be a microprocessor. The Altera Nios and Xilinx microblaze are the two prime examples. Once the processor specified in the HDL text has been instantiated into the real world, it can then be fed instructions written in a relevant programming language, which it will execute, once again, because its structure, such as its program counter, instruction decoder, ALU, etc., determines what's going to do. Well, I can boast of having written my own processor in Verilog, shown here. It's along the lines of Ken Chapman's PicoBlaze, with some advantages and some drawbacks. One advantage is that it's not dependent upon built-in features specific to Xilinx chips. It's portable across different FPGA architectures. Another is that it has a more powerful peripheral I/O scheme. A significant drawback, however, is that it's difficult to use. I don't have a compiler for it. Instructions have to be written as lines of Verilog code that are all symbolic substitutions for constants that get instantiated into memory blocks. Like circuit design, HDL coding practice can be modeled upon the trivium. When the Europeans invented the university system in the Middle Ages, each discipline was divided into 3 tiers of grammar, dialectic or logic, and rhetoric. For a good romp through this, you can see the Hidden Brook Technologies presentation on circuit rhetoric. So the grammar and dialectic elements of writing HDL are obvious, as the discipline is derived from George Boole's mathematics and is often referred to as logic design. But what about the rhetorical element? How does that apply? Well, let's start with this overview. The grammar for HDLs would be and, or, not, XOR, register, 0, 1, clock, nanoseconds, picoseconds, add, subtract, multiply, compare, shift, and so on. These form the basic tools that you're going to need to construct your designs. The dialectic is where your designs are constructed, and what has to happen here is you need to meet the design requirements. It needs to function as it is designed, and it needs to work over a wide range of input conditions. What happens when you throw it a curveball? Does it lock up, or does it know how to hold itself together and continue? Now here's the rhetoric. How well does your HDL convey the intended function of any portion of the design? Is the design hierarchy in keeping with the functional divisions that you have? If another engineer looks at it, is it intelligible? If you look at it sometime after you've written it, do you find it intelligible? So from this summary, we see that rhetoric in HDL coding consists mainly of writing so that someone else can read it and understand it. While there are other layers of rhetoric above this that are concerned with the elegance of algorithm design or the overall coordination of a system's functions, those layers are beyond the scope of our present discussion. Now, an element of HDL rhetoric that goes a long way towards illuminating the function of a snippet of code is something that's often derided by those who work in programming languages, and that's namely the formatting and the flow of your text. They sneeringly call it pretty code, and they say that's bad. It's a waste of time. Well, they have failed to recognize the human brain's outstanding capacity for eliciting understanding through pattern recognition. Text that's aligned according to logic layer depth, that uses vertical space for lists of elements rather than trying to cram that all into one line, and so on, that grants immediate and far better comprehension to the mind than code that looks more like a rummage sale. So yes, the synthesis tool or your compiler won't know the difference, but when you're writing code, remember that you're writing for two audiences, both the machine and man. If the grammar of a piece of HDL is correct, it will be free of syntax errors, and it will make it through synthesis. If your dialectic is correct, it will function properly in both simulation and your bench testing. And if the rhetoric is correct, someone can look at that and say, I know what this written function is supposed to do. Another common HDL rhetorical failure is trying to reduce logic functions to as few operations or lines of code as possible. That's a mistake, because that's what the synthesis tools are for, and they're better at it than you are. Chip capacity is now large enough and synthesis tools are now good enough that it's no longer necessary to worry too much about minimizing your register and gate counts. The synthesis tool will take what you think you've designed, smash it to bits, and reassemble it into something that's perhaps completely unrecognizable to you, but nonetheless functions exactly the way that you designed it. So there's nothing to be gained but confusion by attempting to write extremely compact functions that wind up being perfectly incomprehensible to you. In fact, for the sake of maintaining parallelism or otherwise enhancing understandability, I'll often include degenerate cases or conditions in HDL functions. And by that, I mean things that I know will be reduced or even completely removed during synthesis, because those lines serve as indicators to myself during the design that, yes, I've considered that condition, even though I know the synthesis tool is going to remove it. Those lines of HDL also serve other human readers later by illuminating the complete scope of a given function, or by completing a parallel set that the pattern-seeking mind would find questionable if it sees that the function appears incomplete. Because if completeness is neglected, someone, including the code's own author, will probably at some later time experience the hassle of looking over the code for hours and then finally concluding, oh yeah, I see, I remember why that state was omitted, because it can't be reached. Well, that kind of hassle can be avoided by including those known degenerate cases. When your code is complete, understanding follows more easily. The best approach is to write comprehensive, well-formatted, and readable code, comment it generously, and then let the synthesis tool optimize it for the target IC. That is HDL Rhetoric in a nutshell. Now, to wrap this discussion up, contra the praise for synthesis tools previously mentioned, this excerpt highlights when synthesis tools need to be reined in, and that is state machine reset. Further down in the file that this snippet comes from, state idle is explicitly coded as all zeros. Now, if the synthesis tool settings permit it to extract and reassign FSM states, then state idle just might wind up as something other than all zeros. Depending upon whether your target IC is an FPGA or an ASIC, or whether or not an asynchronous reset is employed, this may or may not be a problem. But it is still best to be pedestrian and explicitly assign states, and not to let the synthesis tool reassign them once you've defined them. And a point of style, one-hot architecture is well suited for FPGA and ASIC targets, since registers are plentiful and routing resources can often be overburdened, while binary architectures are more suited for CPLDs, since their logic interconnect fabric is impressive, but you almost always find yourself short on registers. And note that using the VHDL enumerated type for state variables is best avoided, since that entails specifically not assigning any particular value to any particular state, and therefore always being subject to the decisions of the synthesis tool. Well, I think that's a wrap. Please feel free to contact Hidden Brook Technologies for help with your latest project. And thank you for watching.